Here's what we need to cover today. You should be able to define electromotive force, sometimes called EMF. You should be able to describe the concept of internal resistance. You should be able to apply the equations for resistors in series and in parallel. You should be able to draw circuit diagrams. Describe the use of ideal ammeters and ideal voltmeters. We've already actually talked about that a little bit, but we'll re-emphasize it. Describe a potential divider and solve problems involving electric circuits. Kyle just told me there's an app on his iPhone, right, that does IB definitions. And look at this. Define right here. Again, I will remind you guys, if you look in the syllabus and IB tells you to define something, you should probably know what that is, okay, and probably be able to explain it somewhat. It's good. That word right there tells you, hey, they expect me to know that, and there'll be a question about it at some point in my life. We're going to start with a little demonstration that's going to look like this. So after doing our little experiment here, we discovered that when we closed the switch, bulb A actually got brighter, and bulb B actually got dimmer. Excellent. Now we got to figure out why. Okay, here we go. Electric circuits, you guys. When we're talking about electric circuits, there's lots of different ways to try to visualize it and imagine it and remember it. I personally like to think of the analogy of a circuit being kind of like a river. And the water flowing in a river can be thought of kind of like the electric current flowing in a circuit, okay? If you have water flowing down a river and it narrows and constricts, you usually get some sort of a rapid, right? You get rapids flowing. And I think you can kind of use the analogy that the rapids in a river are kind of like a resistor in our circuit. It is something that slows down the flow of current. What we've been calling potential difference or voltage, you can kind of think of as being like the slope of the river. If it gets steeper, that's a bigger potential difference. If it's nice and gradual, that's a very low potential difference. And you can think of a river, if I have a big steep river, the current's going to go faster. If I have a greater potential difference, the current's going to go faster. So that's kind of an analogy there. And finally, what would, in our model here of river being like electrical circuit, what would the battery be analogous to? What does the battery do to the electricity, and what's that going to have? What does that to our river? What? It's kind of like this. No. The battery is the thing that gives you the potential difference. It doesn't change, but it provides it. So what provides the potential difference in our rivers? What? Oh, you guys are so close. In my mind, and again, this is an analogy, so you can do however you want, but in my mind, it's kind of like the sun. The sun is what puts the water up in the mountains, gives it its potential energy. That's what the batteries and generators do, is that it gives the electrons their potential energy so they can flow, okay? Okay, electromotive force. Electromotive force, remember, in your syllabus, this is a term that you were asked to be able to define. So let's define it. Electromotive force technically is the work done per unit charge by the battery in moving the electrons from the positive to the negative terminal. Basically, EMF is the voltage that is created by the battery. Sometimes that's called EMF. So we have voltage that's created and we have voltage that's used. The EMF is the voltage created so that those electrons can go around a circuit and do stuff. When a device uses potential difference, we say it uses voltage. When a battery creates potential difference, we say it creates an EMF. And actually, there's different ways to create EMF. We can do it through an electric generator as well. Now, a crazy thing about batteries is that they tend to have resistance inside of them, what's called internal resistance. So even though a battery, like this little battery right here is a 9-volt battery, the chemicals in here create 9 volts of EMF, but 9 volts of EMF won't come out of this battery because inside of the battery there's a certain amount of what's called internal resistance. And some of that internal resistance will actually use some of the voltage inside before the current even comes out. As a battery wears down, the internal resistance goes up, and it ends up using all the voltage before any of it comes out, so none of it can be used outside.
So it still creates the same amount of voltage, but it doesn't use it?
Pretty much, yeah. The resistance is so high that the voltage is created by the chemical reactions in there, and so.
Why is there more resistance? Sometimes the sun carries the water up the river.
So the first kind of circuit we need to talk about is what's called a series circuit. A series circuit, and this is oftentimes the most simplest one to deal with. In a series circuit, you have one path, and all of the current travels through all of the devices. In a series circuit, you have one path, and all the current travels through that path. Since you only have one path in a series circuit, the current throughout that circuit is constant. Okay, because there's only one path. The current at the beginning, the middle, and the end, it's the same all the way through. So in a series circuit, you have one amount of current going through the circuit. If you have multiple devices, what will happen is the potential difference, or the voltage, will drop at each device. Each resistor will use some of the entire potential difference that was provided by the battery or by the generator. Okay? So you have one common current, and you have independent voltages used. Guys, if we think about a series circuit as our river analogy, in a series circuit you have one path for the water to flow. The rate of flow, or the current, is going to be the same all along your river. And every time you have a resistor, it's kind of like a rapid, and the river loses some elevation. Okay, so each resistor determines how much voltage it uses. Okay? You got to think of it that way. So this idea of equivalent resistance is important. When you have more than one resistor in a circuit, what will be helpful in solving problems is to find the total resistance of the circuit, or what's known as the equivalent resistance. Okay? So that's the total resistance of your circuit. And when things are connected in series, it's very easy to do. When resistors are connected in series, to find the equivalent resistance, all you do is add them up. Super easy. Okay? Just add them up, and that will tell you the total resistance of the circuit. What you might notice then is if you add a resistor in series, what you have done is you have increased the total resistance of the circuit. Okay? Whenever you add a resistor in series, the total resistance goes up, which means the total current goes down. Okay? That's pretty cool. So again, whenever you add a resistor in series, the total resistance goes up and the total current goes down. And then you use the equivalent resistance to find how much current you have in the circuit, because I equals V over R. Okay? So we can start to solve problems that way by finding the total current. And once I know the total current, that's the current through each resistor, and I can figure out how much potential each resistor uses, because V equals IR, and so on and so on and so on. Let's look at an example. Here is a series circuit. Okay, notice I have 3 light bulbs connected to a battery, and there's current going through here. First of all, let's look at something that should be fairly obvious to you. If one of these light bulbs burns out, what happens? So what happens? They all go out. When you connect things in series, if one thing breaks, they all stop working. Okay? Right. Because your batteries are usually connected in series. And if you only put 2 batteries in, then the device doesn't work. And the old Christmas tree lights used to be wired this way. Right? Back in the day, if you had one light bulb goes out, they all went out. They don't wire them this way anymore, okay, which is nice for us people that deal with Christmas tree lights. Think about your house for a second. Think about your house for a second. When one light bulb burns out in your house, does the whole room go dark? Really? Generally speaking, in most people's homes, when one light bulb goes out, they all don't go out. Sometimes you can trip a circuit breaker, and that's a different thing altogether, and then the whole room goes out. But usually when the light bulb burns out, you just replace that one light bulb. It doesn't make the whole room dark, which should tell you that your house is not wired in series.
Yeah,
okay?
If you're wired in series.
Okay, let's do some simple math here. Let's say we have a 12-volt battery. Let's say that our light bulbs are 2 ohms each, 2 ohms of resistance each. What's our equivalent resistance?
6 ohms.
6 ohms, okay? So our REQ is 6 ohms. What's our current total? 2 amps, 12 volts, 6 ohms, okay? So our current is 2 amps. So if I place my ammeter right here, what's it going to read?
2.
What if I place it here?
2.
And here?
4.
And here?
6.
Okay. 2 everywhere. 2 everywhere.
You were accusing me. I was so lost for
Now let's figure out how much voltage each bulb uses. How are we going to do that?
It's 1/3.
I equals V of R, but in this case we'll do V equals IR. Okay, and this bulb, how much current does it get? 2, what's its resistance?
2 ohms.
How much voltage does it use? 4 volts. How about this bulb? How much will it use? 4 volts. And this one? 4 volts for a total of? Which was what was provided by the battery, and life's good. Okay? One last thing to consider. If I was to measure the potential right here, what would it be? 12. And here? 8. And here? And here? Okay, beautiful. All right? But the potential difference from here to here is what? And from here to here is what? And from here to here? Great. Okay? So there's a difference between potential and potential difference. Okay? Okay, here's another situation. 12-volt battery, 2 different resistors. Okay, we could do the math now if you wanted to. What would be the equivalent resistance?
8. Oh, wait. Oh.
Equivalent resistance, 690 ohms. 690 ohms. Then I could find the current by doing V over R, right? 12 over 690. That would tell me the total current. And then I could find the potential used by each thing. And it would actually look something like this. I'd have 12 volts of potential at point E to point A. I would use 6.8 volts through the first resistor. So at point B, my potential would now be 5.2 volts. Then I would use the remaining 5.2, then there'd be nothing, and then the battery would provide me with 12 volts again, and it would go around and around. So now we're back to those devices called ammeters. Remember that an ammeter measures current. You must connect an ammeter in series, or else it will not work properly. And an ideal ammeter would have no resistance, Now, technically, that's pretty impossible to do, but they have very little resistance. And the reason being, you don't want to affect the circuit that you're measuring, right? So if you place something in series that has no resistance, it doesn't change anything. And then you can measure the current flowing through it, and it's kind of neat. So that's how ammeters work. If you place an ammeter in parallel, it messes things up pretty dramatically. Here's the second type of circuitry that we can have. They're called parallel circuits. Whoops. Whoa. And a parallel circuit is a circuit that has multiple paths in it. Rather than there being one path, we now have multiple paths. In our river analogy, you can think of it as if you have a river and all of a sudden it branches into a couple different paths, and then those paths don't have to all have the same amount of current. They can. You can have some with a lot of current, some with a little current. It all depends on how much resistance is in each of those paths. That will determine how much current goes through each path. The total current through the circuit will be divided amongst the paths, however. Okay? So if you have 3 or 4 paths, if you look at the current in each path, that will be equal to the total current in the main branch of the circuit. And the current that each resistor gets will be determined by that particular resistor. Okay? If all the resistors are equal, each path will get the same amount of current. But if the resistors are not equal, the path that has the most resistance will get the least current. The path with the least resistance will get the most current. Okay, guys, this is where it gets weird. Okay, you can imagine that if you have multiple paths, you can get different currents through each path. If you have resistors in those paths, the voltage that they use will be the same. Okay, the voltage drop across parallel resistors will be the same. If you go back to our river analogy, you think about if you have multiple paths in the river and they go through a rapid, they will all lose the same amount of elevation. Okay? Exactly. Okay, so that's great. So in parallel, all of the resistors that are connected in parallel will use the same amount of voltage.
What if it's different?
So series and parallel are kind of inverse of each other. In series, the current's the same through all resistors, and the resistance determines how much voltage each resistor uses. In parallel, the current varies, and the resistance determines how much current goes through each path, but they all use the same amount of voltage. Okay, so they're kind of inverses of one another. So in order to solve problems, we need to figure out the equivalent resistance when things are in parallel. And it's a little bit tricky, but it's not super tricky, but some people struggle with it because they forget how to add fractions. When things are added in parallel, this is how you find the equivalent resistance. Okay? 1 over the total resistance is equal to 1 over each of the resistors. You have to look for that common denominator. Please remember when you add fractions, you don't, 1/2 and 1/3 is not 1/5. Okay? You have to find that common denominator or use decimal situations. A key thing to notice about resistors in parallel. is that when you add a resistor in parallel, the total resistance goes down. Even though you've added resistance to your circuit, the total resistance goes down. Therefore, what does the total current do?
Goes up.
It goes up. Every time you add something in parallel, the total current goes up because the total resistance goes down. Okay, let's look at our little drawing here with our 3 bulbs again. And this time they are connected in parallel instead of in series. Again, the first thing you should notice now is that if one of these bulbs burns out, the other ones still work. They actually won't get brighter. You can do the math. They will actually stay the same. It's pretty wild. Okay, and this is how your house is wired up. One bulb in your house burns out, the other bulbs don't do anything. They just stay the same. Okay, they don't get brighter, they don't get dimmer if everything's working right. That's a whole. So a voltmeter, you guys already know, is a device to measure potential difference or voltage. And we connect it in parallel around the device to measure the potential difference. Or basically, you connect it in parallel between the 2 points where you want to measure the potential difference. And an ideal voltmeter must have infinite resistance. It must have an incredible amount of resistance, because when you add something in parallel, you can try them mathematically. If you add an infinite resistor in parallel, it doesn't change anything. The total resistance does not change. Okay.
If it's in parallel, even if it use it, would it not change anything? Because we just said that.
So here's kind of a pictorial overview of what we've been talking about. Okay, this top one, we have 3 bulbs connected in series. Here's our generator. It provides an EMF, which gets used by the bulbs. They will each use a fraction of the total voltage. Okay, if one bulb goes out, they all go out. Every time I add a bulb in series, the total resistance goes up. Okay, that's the first part. Second part, now they're connected in parallel. Notice there's multiple paths for the electricity to go through rather than just there being one path. If one bulb goes out, the other 2 do not go out. They all use the same amount of potential difference, even though that seems bizarre and strange. They do. They really do. If I add a bulb in parallel, the total resistance goes down instead of up.
Wait, so what's the real use of a series cell?
It's a great question. What's the use of a series circuit? There's a couple different uses. For example, let's say you create a device that needs a certain amount of potential difference or a certain amount of current. Okay. Most electronics, they're all different, right? But we have batteries that are all the same, 1.5 volts. But I don't need 1.5 volts. I need 1 volt. So if I connect some resistors in series before my device, they will use some of that voltage. They will slow down the current, and it's called a potential divider. I can divide the potential difference so that my end product gets what it needs. Okay.
So instead of just making batteries.
Let's look at just kind of a basic way to think about solving problems here. First thing you want to do with a circuit is find the total resistance, the equivalent resistance. That's a good thing to know, because that's a good starting point. When you find the equivalent resistance, you know the total EMF provided, and the equivalent resistance, you can find the total current. Once you've found the total current, you can calculate the individual potential differences used, or the individual voltages used. And then if you have things in parallel, you can use that also to find the individual current through each path. That's kind of the mindset you want when solving circuit problems. Okay, let's go back to our original situation now. Let's go back to our original demonstration at the beginning of class. Even though I used a 9-volt battery, we're going to pretend I used a 6-volt battery. Okay? And let's imagine that each of those bulbs has a resistance of 2 ohms. I don't really know what they are, but they are similar. When the switch is open, what is the total resistance in the circuit? When the switch is 4 ohms. Okay. So R is 4. Okay. What's the total current?
What's 24?
I equals V over R, right?
1.
Okay. 1.5 amps. Okay. You with me? Okay. How much voltage does this bulb use?
4.
3 volts. And how much does this one use? 3 volts, because it's just a series circuit here. It's just got 2 bulbs. They're equal. It divides the voltage. Life's good. Let's figure out how much power they are consuming. How much power by this bulb?
6.
Yeah. 4.5, right? 4.5 watts. And this one is also 4.5 watts. Okay? They were equal brightness, right? Now when we close the switch, everything changes. Now this is slightly different than what we've been talking about in class because I have a parallel and a series circuit together. So some of the things that we talked about won't be the same. Like when I said when you add a bulb in parallel, it doesn't change the brightness of any of the bulbs, but you guys noticed that this bulb got dimmer, right? That's because there was another bulb in series with it. If that one wasn't there, it wouldn't change anything, which we'll try in a second. But let's do the math. We close the switch. This is where it gets a little bit tricky. What is the total resistance of these two bulbs in parallel? The resistance. Here, 1 over 2 plus 1 over 2.
2 over 1.
It's 1 ohm. Sorry, Renee, I just don't have another color to choose from. I could do red. So that's 1 ohm. So what's now the total resistance of my circuit? This acts like a 1 ohm resistor and a 2 ohm resistor. So my total resistance is now 3 ohms. Okay?